So this is me. I'm going to talk about InDatabase Hadoop. I'll try to stay away from product. I'm going to talk about technology and also the implementation. So this is the agenda. Very briefly, an overview of big data, MapReduce, etc. And then InDatabase MapReduce as a concept. What is this? Okay. And then I'm going to deep dive into the Oracle's implementation of InDatabase Hadoop. I need to pick one implementation to talk about the concrete case. That's the case, but I can assure you it won't be product pitch anyway. And then give a demo and tell you, what we're thinking for the future. This is our legal disclaimer, which says, if I talk about anything which is like part of the future product, you cannot go to court and say, oh, I bought this because I heard this guy talk about it at Java 1. So you cannot do that. Garrett is not here yet. Garrett Schwartz, he's the architect, and he's the one who had a PhD intern from Yale. His name is Shui Yun, and he worked under the direction of Garrett to build a prototype. And they presented the prototype at Sigma 2012. And you can see the link there. And so you can read the whole paper online. It's all the details of the implementation. And now we are in the process of going from prototype to product. So we're going to productize this. And in the next 12 months, as this is the usual language we're using now, it probably will be available as a product, but I'm not going to talk about product this afternoon. Anyway, so big data, the big picture. So when people talk about big data, they usually refer to the left side. Yeah, must be the left side column, non-relational stuff, where you have, mostly unstructured data, and the storage varies from file system like HDFS or NFS to key value stores like NoSQL databases, to document databases like MongoDB, to GraphDB, and to Google's Bigtable, etc., etc. So it's a variety of storage, and but it does not include RDBMS. So usually when you heard big data, they're talking about anything but RDBMS in terms of storage. And then they usually tell you, big data, it's 3 or 4 V's, the volume, the velocity, which is, fast acquisition of data, and the variety. Variety means, data comes from, sensors, meters, call details, web traffic, web logs, social media feeds. Those are the most common data that you find in the big data literature. They want to stress those data. But you can also have special data, graph data, text, images, audio, video, metadata. So variety is a key keyword here. And then volume, to go from terabyte to petabyte to exabyte, I have not seen any exabyte, but people talk about it. Then the value or the density, it means the content of each individual data is very low. It has almost no value. What is the value of a tweet? If you lose a tweet, who cares, So it's low density. And then the analysis model, it starts with, programming model, the MapReduce programming model, and then it translates into Hadoop implementation. And then now people are now adding a little bit of declarative on top of Hadoop, so you have Hive and different approaches to simplify, to make it easy for non-Java gurus to be able to do MapReduce as well. So that's the story of big data. Now, we are claiming that not only Oracle, many companies, mostly RDBMS vendors, but also research companies, new startups, like Hadoop, HadoopDB, and some others, they are claiming that RDBMS is also part of the big data story. Okay, so when you look at the RDBMS, which is the other column, you can see that the storage is RDBMS. The velocity can be low to medium. You don't use the database to do high acquisition of sensor data. You can do it, but, limit. And then in terms of variety, we can see the databases storing, call details, spatial data, graph, audio, images, metadata, sales record, those are business data, sales record, the financial data, medical data, intelligence data. And the volume can go from terabytes to petabytes, okay? And the density or the value is high. A record in RDBMS can be worth, millions of dollars. It's a transactional data. Okay, so it carries high value. And then the analysis model can be declarative. Mostly databases have been providing you SQL functions, analytics functions, aggregate functions. Those are declarative. It means you don't have to write code. But those are not enough to do very complex MapReduce operations. So that's why all those vendors, RDBMS vendors, you will hear like Astrodata, some other, many players, and newcomers are claiming that we can add programmatic MapReduce to the RDBMS as well. Okay, so that will be my focus for this talk. Okay, so what is the concept of InDatabase MapReduce? The concept is to apply MapReduce techniques to data stored in relational database, So it could be a SQL MapReduce, as I call declarative MapReduce, but it could also be programmatic MapReduce. That's why I put this yellow elephant there. That's Hadoop in the database, and that will be the topic of my talk. So why are we doing that? We have seen customers, a lot of customers, moving business data, data stored in relational database that can be qualified as business data. They are moving those data onto Hadoop clusters in order to apply MapReduce techniques, to those data. And we all here know that data shipping is a bad idea. So you don't want to do that. What you want to do is function shipping, so which is, bring Hadoop to the RDBMS data. It has a lot of consequences when you're shipping data to Hadoop cluster, not only in terms of space. You need 3 times the storage in any Hadoop cluster. You need 3 instances of your data for high availability reasons. There is no straightforward way to export data from relational databases to Hadoop clusters. There is a Scoop and some other tools, but they have issues. And for example, Oracle does not provide any tool. There is no official tool to export data from Oracle to the outside. We want your data in Oracle, not the other way around. Okay? And so we also want to leverage RDBMS declarative analytics and BI tools. There is a typo there. And then, as I said before in the previous slide, extend RDBMS with programmatic analytics. And the other thing we might consider also is put MapReduce analytics closer to OLTP, which is where the database operations happening is OLTP. It means like you will be doing checkout at the register and maybe look into a pre-processed data for fraud or things like that. So it's not exactly real time, but it could be near real time. So you can refresh those data very frequently, and then during the OLTP, you can just click and find out what's going on with this credit card or this customer, et cetera, et cetera. So in InDatabase MapReduce, so there are a lot of initiatives. As I said, we are not the only one thinking about that. So you have Hive, Big Latin, which is more a language, but anyway. And then TenSync from Google, then SQL MapReduce from Teradata / Astrodata. Then you have Hadoop DB from company Hadoop. And this comes from Yale. You know, those are research people from Yale. Now they created a startup, and they are, you know, prototyping and selling this engine. You have MongoDB, who have added Hadoop or programmatic interface to their database. And they have a booth in the exhibition hall in Moscone South. I should stop by and ask them what are they doing in the Hadoop world. And then, okay, so, but the limitation we have seen, you know, look at all those implementations. I'm not saying that all of them has those limitations. I'm saying that you will see those kind of limitations. So the first limitation is you probably will need to rewrite the Hadoop program in a different language. I mean, they do not support Hadoop as is, your Hadoop mappers and reducers as is. I'm not saying that all of them are in this situation, but I'm saying this is one limitation you will find. The second limitation you will find is they have a dependency on a Hadoop infrastructure, which means in addition to the RDBMS, maybe they sell you one box, but in the box you have RDBMS infrastructure and you also have Hadoop infrastructure. And they load data dynamically at runtime from the storage, from the RDBMS storage to the Hadoop infrastructure. So it's not technically the same infrastructure. It's two infrastructure combined and sold as one. So those are the limitations. Now the question is, can we do better? So now I'm going to talk to you about the Oracle's implementation of InDatabase Hadoop. So the product name will not be InDatabase Hadoop. You know, the product name is different from that because the product has SQL MapReduce and InDatabase Hadoop. Okay, so but I'm not going to talk anymore about the product. So what are our goals and what are the features? So the first goal, and as everybody, is to process data in place. You know, no need to ship data to RDBMS to a separate infrastructure. We have implemented the notion of Hadoop container in the database. So I know you guys are Java guys, so you're familiar with J2E, J2E container, etc. So think about this. In J2E world, you have a container, you drop your beans, your J2E beans into the container, and it just, okay, you need to do some configuration, and then it works. And you can move your beans around to any J2E container. So here we're doing the same thing. You know, we're trying to have inside the database, really inside the RDBMS, a Hadoop container. So you can move your Hadoop mappers and reducers from anywhere, okay? You can ask, yeah, because, yes. No, okay, in the initial slide, I explained that Hadoop use different storages, and it's not necessarily file system. The storage can be anything. No, we are reading from tables. I'll talk about it. No, we're using traditional database table. Oh, okay, okay. So the question is, at the end of the day, database storage is done on top of a disk drive or some sort of storage. Sure, but it's not a file system. Yeah, what I'm trying to say is that we are using natively the RDBMS table. So this is Garrett Schwartz. He just entered the room. I already introduced you as the father of the project. So you want to raise him your question? I'm just saying that we use RDBMS storage, you know.
Yes. So the model is that if you're deciding to run Hadoop inside the database, it's probably because you have your data inside the database. And if you have data inside the database, where are you going to store it? You're probably going to store it in a table.
In tables, exactly.
So the idea is that we take the data that's available in the table and we make it available as Java Hadoop writable objects.
As Java objects.
So that you can, that your mappers and reducers can read them. And that's the sort of basic idea of how do you connect, SQL with Java is that we basically take a SQL row.
But it's still not a native Hadoop store.
There's no HDFS.
But
HDFS to be found.
So I think when we get to the implementation details, we can talk more about this thing. So the next thing I want to talk about is the source compatibility. We accept Hadoop mappers and reducers as is, and that's what I just explained. We have a kind of Hadoop container in the RDBMS. So you can bring your Hadoop mappers and reducer from any Hadoop cluster, and with some configuration, and I'll show you the configuration in the demo, you can run those in the database. So we have a Java interface, which means a Hadoop developers who knows how to invoke Hadoop jobs the traditional way, the traditional Hadoop way, will continue to do that with a little delta of how to invoke Java in the database. There is a little bit of change, okay? But that's it. And then we also have a SQL interface, which means we can have map and reduce steps in SQL statement. I'll show you, and I'll demo that as well. Okay, so how does it work? I'll just show the whole picture. So this is kind of our Hadoop container. And what you're seeing here is each box is a parallel query slave. So we use the parallel query engine inside the database. The parallel query is a mechanism by which you can fire up a query, and it will fire up multiple query slaves to process the query. Okay, so in this case, what we're using is we are using parallel query. So each box is like a query slave. And then inside each box, we are running a pipeline parallel table function. And on the top, the table functions are your Java mappers, are the mappers code. And in the bottom, it's the reducers code. It's your Hadoop mappers and reducers that we are running as parallel pipeline table function. And then the shuffling is done by the partition by cluster by close, which uses some hash function to route data with the same keys to one particular query slave, exactly as a Hadoop framework does when you get data from different mappers and you shuffle to the reducer. Okay, good point. The question is, do we have a restarter mechanism? No, we don't. But traditionally, RDBMS does not run on cheesy box. It runs on a robust and reliable box. So this might be a minus in our case, but we do not have a restartable mechanism as we speak. You want to add something to that? Okay.
Yeah, so I mean, basically, everything you know about Hadoop other than the API is basically been turned into SQL. So it basically runs on the SQL engine. There's no task trackers. There's no job tracker.
No data node.
There's no data node.
Right.
Yes, so there's nothing that sort of says that SQL cannot be restarted if there's a failure in a node. But in fact, the Oracle implementation of parallel query, if you have a node failure, what happens is that query, the database will stay up, but that query will error out.
Needs to be restarted, right?
And restart it. So
from the beginning, you restart from the beginning
of that particular statement. That's a theoretical possibility that you can have a SQL engine that can be restartable if you have a failure in a process. The Oracle engine basically just
doesn't fail, so you don't need to. Why would you want to fail?
Yeah, that's what I'm saying. People have been using it to do business for ages. It might fail. We should be honest here. It might fail, but you need to restart. So we don't have this restartable mechanism. Our container does not have that. Okay, so those are the pieces of the architecture. As you can see here, you start with a SQL query, it's like select something. But even if you don't start with a query and you invoke the Java interface, at the end of the day, it is a SQL operation, because how do you start parallel query? Well, by sending him some sort of SQL. Okay, so we have the query engine. You can see the mappers here and the reducers on the top. You have the table reader and table writer. So those are implementation of record reader and record writer, those interfaces. So which makes transparent to the Hadoop mappers and reducer the notion of table. They don't know they're reading from table. They're just reading from some data source. Then we have a Java VM in the database. People know about the Java VM inside the database. No, it's been around since release 8i, okay? And I have one slide to explain how it works. And then you have the data storage. So we can get data from a table, from XML table, and also object view. That's the bottom line. So we do the type mapping, task execution in the JVM, and the partitioning and task scheduling is done by the PK engine. Okay, so now we're going to zoom into a specific part of the implementation. So for this implementation and the thing I will demo here, use the new, the upcoming Oracle 12c database. We're using the VM in the database. The VM in the database, you have the choice when you create the database to pick which JDK you want. If you want JDK 6 compatibility, or if you want JDK 7 compatibility. Right now, we're using Hadoop 0.22. So this is the most stable. Do you want to comment on why we're using Hadoop 0.22? I think it's the most stable by the time we started the project.
Yeah, and basically it's the AP. Remember, it's only the Hadoop API. So it's basically what you need to write your application. It's not the underlying engine, because we basically replaced the entire engine with our own engine. But it does have the when we created this this Java environment, we basically cloned 0.22. That's not to say that we can't make a new one with other versions of Java and be able to reuse the code, but that's the one we release right now.
What was the question?
Distributed cache.
So the Oracle database is a shared everything database. So the distributed cache can just be stored in Oracle table that's accessible read only to all the slaves.
So you're telling me I have to take some single thing that I was using?
I'd like to repeat the question for the others. What was the question?
The question is, so you're making me take some external file like CSV and forcing me to put tables like that and it becomes distributed cache
Well, Oracle also has a file system called DBFS, which is, if you want to store your things in a file system, this DBFS file system is available throughout the Oracle database and actually even externally. So if you want to keep things in a file and you can configure DBFS, then we can access that uniformly throughout the system. You can also, if you like NFS, Oracle can use NFS and you can store your things there and you can get access to that. The nice reason to put it in table or DBFS is because Oracle has a distributed cache for that. If you have your file and it's in an NFS server, well, then everybody's going to beat up on that poor NFS server. If you want a distributed cache, you have to store it in an Oracle storage format, which is either DBFS, which is our file system, or inside of a table. So if you have a CSV file, so this is oriented towards customers who like SQL and who like tables. And in fact, what you're trying to do is you're trying to get portability of your Hadoop application so that they can run inside of your native Hadoop infrastructure, but then also be able to run them inside your Oracle Hadoop infrastructure. And so So usually, if you're in an Oracle Hadoop infrastructure, you're probably a SQL kind of guy, and so storing things inside of tables actually makes you feel all nice and warm and fuzzy rather than making you feel black. So the assumption is that tables are what you really like, and so storing things in tables isn't a problem for you. But we also, inside of Oracle, have, if you like file systems, we have a file system that, oddly enough, do you know how we implement the Oracle file system? In a table. Yes.
Okay. So I need to keep going. So in terms of configuration, we will show you how to do the job configuration. It's exactly as a Hadoop job config, plus some data type. You need to specify what are the types of the key and the values, the input key and values types. I mean database type, what are the SQL types to which you map those things. So for each job, we create a config object that we store in table, of course, in the database. So we have ways to retrieve this row for each job, you know. So we can pass this information from SQL to Hadoop or back and forth. So that's how we handle configuration. In terms of mapping, as I said before, we re-implemented the table reader, record reader and record writer. And we have our table reader and table writer which implement record reader and record writer. Okay, so that we use those to do the mapping between Hadoop types and SQL types. I'm not gonna get into the details of the mapping, but the framework that we have does take care of the mapping, you know, between Hadoop types and the SQL. We might need to do some optimization later in the future releases, but for now it works well. This is the architecture of Java in the database. What you're seeing in the top are the database processes, you know. And Oracle has different architecture, but the most commonly used is what we call dedicated server, which means each user, each client of the database has a Unix or Linux process which is attached to it, or a Windows thread if you're using Windows. So in each of those process and thread, we have what we call a session, database session. Database session runs in a process or a Windows thread. So it has a memory, it has its own memory, we call it the PGA, Program Global Area. Okay, and that's where we instantiate the Java VM. So each user has sort of his own private Java VM, which run in his session. Okay, you might say, oh, isn't that too overhead, lot of overhead in terms of memory, blah, blah, blah. Then look at the bottom picture, the bottom part of the slide is what is called the Oracle Databases Shared Global Area, which is a huge shared memory that all the sessions have access to. All the processes can access this shared global area. This is where we put the system classes, you know, which make the Java VM, and also application classes. So all those classes are shared across all sessions. So if on your machine you have 8,000 users, and we do have customers who are using Java in the database, and they scale up to 8,000 concurrent users doing all Java, which means they have 8,000 sessions, and they're all sharing the same system classes, the VM, and the same application classes. That's how we amortize memory across all the sessions. More sessions you have, less memory per session we consume. So this Java VM scales very well, provided that the machine, the framework, I mean the infrastructure has the resources. So the limit, the system is the limit. Okay, the VM scales very well. That's why we base this Hadoop implementation on it. And this is the pipeline table function. So pipeline table function, this is not unique to Oracle. I think a lot of RDBMS has this notion of pipeline table function. So what it does is it can take a stream of data as input and produce a stream of data as output. So think about Mapper, for example. It's going to receive its input from the actual table, that the parallel query will dynamically partition. So the partitioning in our case is dynamic. We don't have files, separate files for each. We dynamically split depending on the degree of parallelism you specify. So each PQ slave will receive its stream of data from the input table, will produce an output that will be consumed by the reducer. So those are pipeline table functions. They can receive a stream of data, produce an output of data, and we know inside Oracle, inside the Oracle SQL, how to treat the stream as a virtual table. And I'll show you an example where we can run a SQL query on this virtual table, which is the output of the stream of the parallel pipeline table function. And so I think now pieces are getting together in your mind. You can see the PQ slaves running the mappers and reducers, and they can receive input either from the table or either from a stream, another pipeline table function, and they can produce an output that can be put into a table. So we can recoup the output of the reducers and store them in a table. So we read from the table to feed the mappers process feed the reducers process and feed an output that we can just store in a table. So we can keep the output of the reducer this way, okay?
So this facility has been around there, available in PLSQL for all you PLSQL programmers. This is PLSQL 1, right? It's been around there for a long time, except we decided, hey, why not make it available to Java programs? And if you're going to make a parallel infrastructure available to Java programs, why not make it match the Hadoop API rather than some other crazy API we might make up? That way you have an immediate base of people who actually understand how to write to this thing and a certain amount of portability of programs between different infrastructures.
Okay, so now we talk about the implementation. Now, how do you use it? And how do you do the configuration and things like that? And what are the different interfaces? So just a summary, and then I will show you through a demo, which is more meaningful than I'm talking. We have two interfaces, as I said. In the left, as you see here, select star from table. And what this is doing is, I don't know if this is working, but the other won't see it. So let me just say, the select star from table is selecting the output of the reducer. So the reducer pipeline table function, the name is hreduce_jp_word count. This is the reducer of the word count job. Okay, so what you're seeing here is that we are making explicit to you the name of the pipeline table function, so you can use it within SQL queries. So you can use the Hadoop jobs, the steps, the reducer step or the mapper step explicitly in SQL query. So that's what we're doing here. So the SQL interface, that query is selecting from the output of the reducer. And you can see the reducer has a configuration key, which is where we store the configurations. And the reducer is getting its input from select star from table hmap_jp_word count, which is the mapper. So the reducer is getting its input from the mapper. Okay, the mapper now is getting its input from the input table, select star from in table at the bottom of the box on the left. So in this query, you are invoking the Hadoop mappers and reducers, and you're selecting from the output of the reducer. You can do whatever you want with that. So what I'm trying to say here is that in any language, provided somebody has written the Hadoop mappers and reducers, from there, from any other languages, you can use those and do some query and invoke those operations. So it is universally available because it's a SQL interface. PHP can invoke it, Python, Perl, anybody.
And you can also, and when you're designing your SQL query, you oftentimes will have your own custom mappers and reducers, but there's a bunch of boring junk you want to do too, like renaming some columns, adding 3 to something, whatever. Well, that you can just do in SQL, and so it basically mixes the sort of usefulness of, say, Pig and Hive, where what you want is a scripting language to invoke your mappers and reducers, but what's the best scripting language for invoking data transformations? SQL. And but now you have SQL now augmented with MapReduce to do the stuff that SQL doesn't know how to do, because SQL is not Turing complete, and that's actually considered to be a plus because it's actually is rockable by an optimizer. But now you can extend your SQL with maps and reduces to make it understand new data types, new kinds of algorithms that SQL doesn't understand. And now you get to use SQL to script together your complicated stuff.
So speaking of optimization, that means that everything that comes out of the reduce is non-indexed?
That's correct. It's basically
correct,
it's a stream following the usual sort of MapReduce paradigm. Now, of course, you can take the output of any of these things and store it into a table.
And then index that table.
Yeah.
And that's where I talk about near real-time OLTP, is that the output of the reducer can be used from some OLTP application where you can just use an index and query this credit card information and see what's happening. So that's the SQL interface. The Java interface is on the other side, and you can see this is the classical job init, job run, Hadoop thing. Now let me show you those things we've been talking about for a while, and I'll start by showing you the configuration. So this is the VirtualBox, and if people were in my hands-on lab session yesterday, you will play with exactly the same thing. So this is let me show you the file. This is the configuration of sessionization job. A Hadoop sessionization job. Sessionization is a very common use case in Hadoop where you want to find out, how many sessions and the guy and how much time he's spending on my website, blah, blah, blah. So it's a very common use case. So this is, let me go right. This is the static method. This is the run method, okay? It's very important to notice that. Okay, you can see here, this is the job configuration. We are naming this job sessionization, as you would do any Hadoop developer. And this is the Hadoop mapper classes. Okay. It is the standard Hadoop mappers. You can get it from Apache demo, or you can get it from anybody. You can get it from any Hadoop cluster. So it's unchanged. Okay. And then this is the class of the reducer as well, over here. Okay. And although this is the input key class, the input key value class, the output key class, the output key value class, all those standard Hadoop. Okay. Here we are adding database things. We're adding database things. We are telling what this is the SQL type which corresponds to the output key. And this is it's a varchar 2 in this case, varchar 10. And this is the number, SQL type number, which is the SQL type corresponding to the output value of the key. And also we are specifying the degree of parallelism here, how many mappers and how many reducers. This is how you control how many query slaves will be fired by the PK engine. Okay? And this is the job init and job run. Mm-hmm. So this is a configuration. Now we will load the configuration in the Oracle database. This is how you access Java in the database. You load the Java class inside the database. Okay, I have already loaded the class. Okay.
And not all these things have to be specified. Like, for example, degree of parallelism. Oracle has a feature called auto DOP. So if you don't specify it and you've enabled auto DOP, it'll try and basically take over your entire machine, or use whatever percentage of the machine you decide to give it to it.
Exactly. So in this demo, what I'm doing is I drop the table, I create the key value table, okay, and then I'm populating the table with some cheesy value. It's a few rows, okay. And then we are calling the the configuration, a method in the configuration to generate the configuration. So remember, we need to generate the configuration key and store in a table so that between Java and SQL we can retrieve the configuration and use it to process the mapper or the reducer functions. So what you're seeing here is that in order to invoke Java in the database, you need to create a wrapper. This is the wrapper. And this wrapper will invoke this method, which is the run method in the function I show you here. So this is the method we are using, public static void run. This is the method we are invoking. And in that method, we will be invoking job init, job run. So when you call this interface, okay, from any language, once again, you are invoking the, you will trigger PQ, you will execute your Hadoop job. Okay, so that's what we're doing here. That's what the demo does. So when I say call sessionization here, I am invoking this Java method from the sessionization class that have been previously loaded into the database. Okay, so let me run this. So I'll just execute sessionization. Okay, so it will process every SQL statement I just showed you. It will drop the table, and then you insert rows in the table, process, and you can see here the output of the reducer that we store in the table. That's it. Okay, next, I want to show you also the SQL interface. So that was the direct, Hadoop direct interface. Now let me show you the SQL interface, and we distinguish this by calling it conf. So conf means we invoke a function to insert the config object in a table, and then notice that here we only have job init and job put. There is no job run. So we are just inserting the config object in the table. Now, when you explicitly invoke the mappers and the table functions, which implement the mapper and reducers, that's where you're gonna trigger the execution. So we are not executing here, we are just creating the configuration object and storing. So this is what this configuration file does. So same thing, we're gonna load this configuration file into the database, and we will invoke it, we will create a wrapper. So if I show you the wrapper here, sessionization conf.sql. So same thing here, we're dropping the table, creating the table, inserting rows in the table, exactly the same rows, and then we are invoking this sessionization conf dot job key, the method job key, and then we call the sessionization into conf key. So when we do that, the configuration key will carry the entry of the row, and then we can read the config object from there. Okay, so this is the SQL query, SQL statement, which is invoking the mapper and the reducer. So what this statement is doing is inserting into output table the output of the reducer. Select star from table H reduce sessionization with the configuration key is inserting into the output table the output of the reducer. We are treating this as a virtual table, and we can store in a physical table. And then the reducer is getting its input, select star from table, from the mapper, okay, with the configuration key. I can execute it, but it should give the same result. Otherwise, I'm doing. Okay, so we should see exactly the same thing happening. Okay, so that's good. Now, what is powerful about the SQL interface is not only the ability for any developer in your company, you tell him, hey, this is the name of the Hadoop steps. You know, the mapper, this is the name of the table function, the mapper. This is the name of the reducer table function. Go and use it whichever way you want. Okay? Well, it is even powerful because look here, I am combining multiple steps of two jobs, two Hadoop jobs. So if you read from the top to the bottom, I'm selecting from the output of the reducer of job number 2, which is getting its input from the mapper of job number 2, which is getting its input from the reducer of job number 1, which is getting its input from the mapper of job number 1, which is getting its input from an actual table. So you can combine whichever way you want, and the good thing about this approach is there is no intermediate materialization of data. You know, as in the classical Hadoop world, you want to do two jobs, you need to do the first one, it will write to the file system, and then you will read from the first one. Okay, go ahead.
So would we be right in assuming that there's no data provided to the outer part of the query until the reduce is complete? There's no like row none feature that would allow you to get an early view of the data? Or you have to wait for the
Oh, no, you don't have to wait. Parallel pipeline table function, you don't have to wait for the completion.
Well, I mean, except where there's a blocking step in the computation. So, like, let's say it was map. Well, then everything can just flow through. The trouble with reduces, as everybody knows, is that you've got there's some dependencies there, and so in fact, things will build up, and if the amount of data is big, then we spill to what we call temp areas and stuff like that. But they aren't part of the user's model. It just happens because you happen to run out of memory. So there's no magic, unfortunately.
Mm-hmm. So I just did a demo, and this is a summary of what we have done so far. Run to reference the database to Hadoop closer to LTP, integration with SQL. And we are looking into, we have input pharma will be available when the product is available. Enterprise security, and this is easy for DBAs. DBAs, they don't need to know anything about Hadoop cluster. You just tell him, deploy this job as you usually deploy SQL jobs. And enterprise developers, they don't all need to learn Java or Hadoop. You can have a key Java developers, you guys will write the mappers and reducers, and everybody else can consume what you have written, through the SQL interface. And then looking forward, Garrett, I'll let you talk. So what are we doing? We're looking forward and we say, well, we can accept mappers and reducers from R engine, R enterprise R, where you can do advanced statistical analysis. They can produce Hadoop code, and we can consume those. Go ahead.
Well, I'd also just like to, I'd like to talk more about what we do today, which is the input formats and the Hive catalog. So we can basically go in and access that kind of stuff. So basically, wherever your data is, the model that we're aiming for is we'll support you in whatever language you want to use. If you want to use SQL, if you want to use Java Hadoop, if you want to use R, if you want to use XQuery, basically whatever language you like, we want to support you accessing whatever data sources you want to access, whether it's HBase or NoSQLDB, or any of the other data sources that might be, or even Oracle tables. We want to be able to access those, and on whatever infrastructure you want. So you want to run an Exadata, you want to run on the big data appliance, you want to run on your own, home-built IKEA, do-it-yourself Hadoop system. You can do it that way. Yeah.
Okay, so that's what we're looking at, supporting more classes, more Hadoop interfaces on output format, and maybe do some more optimization of the mapping. That's what all I have. We have, I think we have 5 more minutes to take additional question if you have. Yeah, we have 8 minutes.
Do you guys have any metrics or benchmarks?
We're doing that internally as we speak. We're not public yet. Oh, that was the questions? Okay, other question?
So you mentioned curiosity about what Mongo does. Mongo actually in the Hadoop space does the same thing, except they don't do it inside Mongo. They have input and output formats that go straight to the Hadoop database.
Exactly.
Any intention of offering up that capability so that if you had a Hadoop cluster, you could read and write straight from Oracle using what you've already built, essentially?
So we can we already have these things called the big data connectors.
Right.
One direction.
Well, I mean, reading is important. Why would you want to, why would data want to go back? It's, you know,
remember what I told you. We want
it's so
your
nice and
data
warm inside of
Oracle.
Inside of Oracle. Why would your data want to go out in that cold Hadoop world? We are looking at that, and especially in the big data appliance market, where basically it sort of smells enough like Oracle. There's likely to be more.
But with output farmer, we should be able to do that.
Yeah.
When we have output farmer, we should be able to do that.
Yeah.
Any other question?
How does this impact the CPU on the database node?
This does run on the database. This runs in the database node.
Right.
It in fact runs in the same processes, and that's one of the things. It's not a two-process solution where you've got your JVM and you've got your Oracle process. The JVM is in process, so you don't have the sort of the context switching overhead. But
it depends on the complexity of what.
Yeah, so if you write some sort of image processing library that goes over pixel by pixel, and you want to run that on your Exadata system, you know, we'll be happy. Yes, do it. Yeah. But you know, so the idea is that we aren't sort of saying that Hadoop, you know, all your Hadoop systems, throw them all away, because this is more of, hey, I want to run it on the infrastructure, I want to run it on my data is already here. If you've got, let's say, 5% of your load is Hadoop, you know, why should I be forced to buy a Hadoop system for 5%?
Right, exactly.
But if 95% of my load is Hadoop, I'd be sort of silly to run it all inside of Exadata.
We'd be happy to sell you the big iron.
Yeah, we've got bigger iron stuff, but it's, you know, then you want to use the infrastructure that's optimized for the, you know, that's the cheapest one for the particular environment you happen to be running in.
Okay,
So
one more question. Your examples had a select star from the input table.
Yeah.
Is that how you would always do it, or would you do?
Oh no, you can select whatever.
You can do whatever you want.
Yeah.
But those are virtual tables, so you really want to store everything and then do whatever you want afterwards.
I think of tables that have millions of rows in it and doing something like this.
Oh, well, millions of rows is fine. It's millions of columns. You know, you never have millions of columns. You can have thousands of columns. But let's say there's, you know, people do have tables, like especially SAP tables and stuff like that, that really have a zillion columns,
right.
And you want to pick out the ones you want, and just because basically if you give too much data to the Java app that the Java app doesn't look at, you know, you're wasting a lot of cycles moving data around. So you want to just select just the pieces that you want to that your app wants.
Go ahead.
Yeah, so like since everything is running inside the DB, say I have my transactional system where I usually run my search queries and all, which needs to be really fast for the transactions. And say I also want to give some data analysis, like say some graphs and all, which we can say that, okay, you can schedule your jobs, or you can ask for a graph and we'll mail you back some PDF or something like that. So if I run those as MapReduce, like in your database, so they would kind of be affecting the regular transactional stuff that...
But this is one of the wonderful things about RAC and Exadata, is that we can use the same infrastructure for both OLTP and BI. And this is irrespective of whether you use Hadoop or just use SQL for BI, because it's a big market, and you know, we don't want to force you to buy two different systems. You know, that we'll sell you two different systems if you want to. But if you want to use the same system for both, we have these things called RAC services, and what you do is you submit your BI queries, and they basically can make sure that they don't interfere with your OLTP SLAs.
So like they be directed to different racks?
Oh, well, different instances within the same rack.
Right, different instances.
Yeah, different instances.
That can be done.
Oh yeah, that can be done, and that can be done for any BI versus OLTP, because BI and OLTP, they sort of, you know, if you want to do BI against your operational tables, That's quite common because, and then another common thing is you actually put them on 2 different systems and use ETL to move operational data to your BI. So sometimes people have a separate operational database and a separate data warehouse and use ETL to move them. That's great. Then Hadoop would be running probably just in the data warehouse. But if you have dual use databases, then you're probably aware of how to do that properly, which is to set up your SLAs and run your OLTP jobs in a separate, as a separate rack service with a different priority level, so that you don't get exactly that problem where some some data analyst comes in and basically takes down the entire set of resources running their crazy query.
2 more minutes, we can take maybe one last question. Anybody?
So you don't have benchmarks, you don't have pricing. So today,
we cannot discuss packaging. We cannot discuss anything. Remember for this conference, we are pre-announcing, so we cannot say.
So I go back to my director tomorrow or Friday and say, hey, you know what? That's not what we're doing right now, because you just described what most of, you said earlier, you said people have scoop and you're scooping it here and it's a bad idea, but that's what we're doing
Data
right
shipping
now.
is a bad idea, yeah, for sure.
Yeah,
Well, we have big data connectors, moving data back and forth between Exadata and Big Data Appliance or your own Hadoop system. There's some places where it makes sense, where you're going to do enough work to make the transfer basic. The transfer didn't matter. There's other places where it's a lot of data, you're not doing that much computes on it, moving it to someplace else doesn't make sense, about not have the other infrastructure. Basically, we want to give you that option. Do things in place, do things remotely, just like we talked about with operational, separate systems and using ETL. Sometimes that's a good idea, sometimes it's a bad idea. It's up to you, because you know your workload and you know how you can, whether it's a lot of computes and it's worth it to move it. Sometimes it's not. Now, as far as 12c goes, it's not being released right now. We do have a beta program for 12c. If you're signed up for the beta program and want to use this stuff, we'll be all over you.
Too late.
Oh, too late.
Yeah, we're no longer taking application.
Okay.
So I cannot tell you to wait, but I can tell you, well, if you're willing to wait, maybe you.
Well, no, we can't tell anybody. We can't tell anybody to wait or anything. It's just we're just telling you that we're doing something. We're doing something, and it's just FYI.
Right.
At this point.
Okay, thank you all, and enjoy the rest of the event.